Hello and welcome. In this video, we're going to take a look at inequalities. And there are a few different types that we were going to look at, and for each of those types, there's a few different strategies to involve. But first of all, let's take a look at what is an inequality. So an inequality is kind of similar in ways to an equation, except that instead of having two values be equal, we are kind of comparing them. One value may be less than another. So we're going to be using less than, greater than or equal to, or greater than or equal to. Now, what can be a little bit confusing when we come to some word problems here is that in English, instead of saying something is less than or equal to a value, oftentimes we say that something is at most some value. Equally confusing, sometimes instead of saying that something is greater than or equal to a value, we say that something is at least that value. Still means when I say something is at least 2 meters long, then that something is a length greater than or equal to 2 meters. So it's a little confusing. Now, solutions to inequalities may be just a single value, or maybe one or more intervals. It may be all real numbers. It's also possible that we have no solution. And so taking a look here, I've got an example, -3 less than or equal to -5. Well, -3 is actually greater than -5, so this is never true. This, unfortunately, doesn't have a solution. We might have x greater than 3, in which case that is true so long as x is any number from 3 to infinity, not including 3. Or we might have 5x squared greater than or equal to 2x squared, and I know that x squared is always positive. And if I take 5 times a positive, it's always greater than 2 times that same positive number. And that's true for all x. So there's at least a couple different examples of solutions. And as you see, sometimes there may not be a solution. Now, the other thing that's a little bit confusing about inequalities, we do write them sometimes in a confusing way when we want to compare multiple things. And so we can always do a comparison of multiple quantities if there's a logical ordering to them. If that's the case, start with the smallest quantity on the left, and then we're only going to be using less thans and less than or equal tos. So here I've got an example, A less than B less than C. Now, if I've got this going from smallest to largest, then every comparison here makes sense. A is less than B. Okay, so that's one way I can read this. Is already one thing that's important. A is less than B, sure. And continuing on, B is less than C. That's another comparison. But these comparisons are all in an order from smallest to largest. So as a result, I also can see that A is less than C. And I can't be switching signs momentarily. A less than B greater than C. Well, then I'd be reading this as A less than B and B greater than C, but then I've got A with a less than and a greater sign C, and I can't really follow the logic there. So we really shouldn't be ever doing that. It's always best to have all of our inequalities point to the left, where that's the smallest number, and they always open up to the right, and that's the largest number. I've heard somewhere along the lines that some people like to call this sort of like a Pac-Man, this little less than sign, where the less than sign, if it's like a Pac-Man, is always eating the larger thing on the right. That's just another way to think about it. Okay, so let's take a look at the most basic kind of inequality first. Just like equations, we can talk about linear inequalities. Okay, with linear inequalities, much like linear equations, we're not going to see any exponents. We're only going to be seeing multiplication, addition, subtraction, that kind of thing. So we can just be using the basic addition multiplication principles in order to isolate the variable. The only trick here is when you're multiplying or divided by a negative value, then you have to change the direction of the inequality. And that's really the way that we organize numbers on the number line, is that the magnitude of the value is increasing both to the right and to the left. So numbers seem to be getting bigger even if we travel in the negative direction. So we all see that 3 is certainly less than or equal to 5. But if we're traveling in the negative direction, negative 3 is actually greater than or equal to negative 5. So whenever you negate both sides of an equation, it's basically like swapping halves of the number line, in which case you've changed increasing to decreasing, and we have to change all of the signs around. Well, why don't we just do a basic example of a linear inequality? Basic enough, but maybe I'll do an example with a combined double inequality, just so you can see that when you apply the addition multiplication principles, you have to do that to 3 independent expressions when we have 2 inequalities combined together. Okay, in this example, I've got 3 being less than or equal to minus 5 minus 4x less than 7. And so just as a little reminder, this really can be split up into several inequalities. We can see that 3 is less than or equal to negative 5 minus 4x. It also tells us that minus 5 minus 4x is less than 7. And when you combine it, 3 is less than or equal to some value, and that value is strictly less than 7. And as a result, you can see that 3 is strictly less than 7. The stronger restriction here is being strictly less than, not just less than or equal to. And you can see that this last equation here is true for all values of x, which is good. If that was the opposite way around, we had, say, 5 greater than 3, that would be false, and that would make this inequality always false. That's why it's important to make sure we have smallest to largest, because then it makes sense of doing a comparison of the first and third values of this inequality. So be careful. Make sure you've always got this written from smallest to largest, and that all the signs point the same way. Now we want to get x by itself, so x is right here. And in order to get x by itself, let's start with the addition principle. See, we can just add 5. But we have to add 5 to all 3 expressions so that we don't change the comparisons. If one value is less than another, adding 5 to both of them will still maintain the inequality. So now we'll end up with a new inequality. All right, now last but not least, we need to get rid of that minus 4. And since it's minus 4 being multiplied by x, we need to divide by negative 4. Or similarly, that's the same thing as just taking everything and multiplying by negative 1/4. Now, whether you want to multiply by negative 1/4 or divide by negative 4 is up to you, but make sure that you do change all of the signs when you do this. And so you can see I've reversed the signs, but now I've got an inequality where all of the values are actually going from largest to smallest, and the inequalities are all pointing to the right. So we're going to change that and rewrite it so that we have the smallest value. You can see that we're going to use the reverse order, negative 3 less than x, less than or equal to negative 2. Again, make sure that this all makes sense. We've got negative 3 is less than x. We've got the x is less than or equal to negative 2. And we should have that negative 3 is strictly less than negative 2 because that's the stronger of the two restrictions. And this does make sense. Negative 3 is less than negative 2. So it makes sense to have all 3 inequalities put together. And this can be turned into interval notation. A strict less than symbol becomes a round parenthesis, and a less than or equal to sign becomes a square bracket. And we can see that this is an inequality whose solution is an interval. Now, what about nonlinear inequalities? We might have to look at some different types of nonlinear inequalities. Quadratic is a very common kind. We can also look at absolute value inequalities as well. Okay, for nonlinear inequalities, it might be best to have sort of a list of guidelines. And let's start off with polynomials and rational expressions. So really kind of any combination of algebra here. Much like when we were doing equations, it's much easier if you can get everything on one side equal to 0 and factor. Pretty similar situation here. Whether you've just got a polynomial or whether you have rational expressions, move everything to one side so you have 0 on the other. And if you have multiple terms that involve rational expressions, start to combine those together so you get a common denominator. Now, once you've got everything put on one side, start all the factoring you can possibly do. Look for common factors, look for sort of maybe AC methods, things like that, if you have quadratics, etc. Now, once you've got it factored, then you can start to figure out, when does this expression equal 0? When something is equal to 0, it's neither going to be greater than 0 or less than 0. But you can start to then figure out, okay, we might be able to satisfy the inequality inside intervals. If you figure out where it equals 0, that's important. Next thing is also try to find out, by kind of looking at the domain of this function, what values does the expression end up being undefined. And in step 4, we're going to take all of those values where either the expression equals 0 or is undefined and make what we call a sign chart. We're going to take a number line and put all of those values on from step 3. And in between all of those values, we end up getting intervals. And we're going to determine whether the expression is positive or negative in each of those intervals. And once we've got that, since we're comparing something to 0, it's much easier to figure out which of those intervals is the correct sign. If we want to be greater than 0 or less than 0, we figure that out by looking at the sign chart. And then it's just a matter of checking the endpoints to see whether or not we include them. So maybe let's try an example with let's go with a rational expression. Okay, I've got something that looks fairly simple here, and if this was just an equation, then you might be able to cross multiply and simplify, but here I've got an inequality, so it's a little bit trickier. I'm going to start off with step 1, which was simply just move everything to one side. And so we'll get our 3 on the left-hand side. Now, continuing on, before we do much else with factoring, let's try to make sure we get this all under a common denominator. In this case, the lowest common denominator would be x minus 2. So I'm going to take this minus 3 and multiply top and bottom by x minus 2 so that I can combine the fractions. Now, just being a little bit careful about some of the signs here, 6 plus x minus 3x. And don't forget with the brackets here, this is going to be plus 6 and all over a common denominator. Okay, well, now I'm on to factoring, and luckily I've got a fairly simple polynomial in the top, which is just linear, and another simple linear polynomial in the denominator. It's quite possible I could have ended up with some quadratics here, and I would have had to do a little bit more intense factoring, but this is great. I can just do maybe one small thing and factor out a minus 2, because I'd rather have x be positive, and I'm okay with taking the 12 and making that into a negative 6 by dividing by negative 2. Now, start looking at the factors where we may end up getting 0. We can get 0 whenever the numerator equals 0, and we can get undefined whenever the denominator equals 0. So, taking a look at the top factors, well, negative 2 is just a constant, and it can never be equal to 0. But the next factor, x minus 6, can be equal to 0 whenever x equals 6. So let's consider that as being one of our many values to put on our sign chart. And also, this is undefined when x is equal to positive 2. And that's another value that we're going to put onto our sign chart. Now it's on to drawing a number line. We will include these two values, 2 and 6, and make sure that we know that, in fact, we cannot let x equal to 2. And that's going to be very important because our inequality, we can't even make a comparison at the point where x equals 2 because undefined is not something that we can compare to 3 in the original inequality. So make sure of that. Now, for our sign chart, we're going to test this expression and see where it might be positive and negative. And you can see there are 3 intervals. First interval is everything to the left of 2. The second interval is between 2 and 6. And our third interval is greater than 6. And our expression, if we wanted to keep it in this nice factored form, is going to be a lot easier to work with. From here, we can take a look at the individual factors. So in the numerator, we've got a negative value, negative 2. But depending on what x is, we may end up with x minus 6 being positive or negative. So take a look for values that are less than 2 and pick any one that you like in this interval. You could pick 0 because 0 is less than 2 and it's in the first interval. And you could pick 1 or you could pick negative 1,000, any value. But then imagine plugging that in to this function. And our first factor, negative 2, is going to end up being negative, of course. And our second factor, 0 minus 6, in this case is going to be negative. And in the denominator, 0 minus 2 is going to be negative. Now, when you make a product of two negatives, you get a positive value. And when you do a quotient of a positive divided by a negative, you'll end up with a negative value. So in this interval, it appears that we are overall going to be negative. Now, jumping across this divider where x cannot equal 2, we'll repeat the same process. Negative 2 is always negative. Pick a value between 2 and 6 though, something like 3, and 3 minus 6 is negative, but in the denominator, 3 minus 2 is positive. And a product of two negatives, that ends up being positive, and taking a quotient, positive divided by positive is positive. And jumping one more interval over, pick a number bigger than 6, maybe 10 is great, and try that out. Negative 2 times 10 minus 6 is positive, divided by 10 minus 2 is positive, and overall negative. Now, time for the solution. Let's look at all of the inequalities that match our expression. We've been looking at negative 2 times x minus 6 over x minus 2, and we want that to be greater than or equal to 0. It looks like that is going to be the case from 2 to 6. You can shade that interval right in. Now remember, x cannot equal to 2. Well, what about at 6? What happens when we plug x equals 6 in? We plug x equals 6 into this circled expression here. We get negative 2 times 0 over 4, which is 0, and 0 is in fact greater than or equal to 0. So we should be including 6 in our solution, and then we can state that as our interval. 2 to 6, and only 6 is included. Okay, one last kind of inequality to take a look at, and that would be using absolute values. And it's really good to remember that we can view absolute values as sort of a distance. So let's use that to kind of come up with an idea of how to solve absolute value inequalities. Okay, with dealing with absolute value inequalities, there are really just two cases that we would need to look at. And if we know what we can do with these couple cases in order to remove the absolute value, then we can rely upon linear inequalities and nonlinear inequalities to be able to solve the result. So first of all, let's say that in case 1, if we have the absolute value of some expression less than another expression, we can visualize that as being the distance between expression A and 0 is less than some distance given by the expression B. Less than a certain distance means we're going to be traveling to the right, but not quite as far as B. And traveling in the negative direction, we're going to be traveling as far, but not quite as far as negative B. And A is going to be a value somewhere in the middle. And so as a result, we can turn this into an inequality with negative B being the smallest, less than A, and A being less than B. So it ends up actually turning into a compound inequality with more than one inequality stated in one expression. And very similar, if we say that the absolute value of A is less than or equal to B, the only change is that the distance between A and 0 is less than or equal to B. So now we can put square brackets, and as a result, negative B will be less than or equal to A, and A will be less than or equal to positive B. And so that's case 1. Case 1 will end up becoming, let's call it maybe a sandwich inequality. A is sandwiched between the negative and positive values of B. Now case 2 is where we switch the sign around. The absolute value of A greater than B means that the distance between A and 0 is greater than B. Now that means that we have to travel farther away than just B. B will be some value that's over on the right hand side. Let's say negative B will be on the opposite side. And we're going to be looking at values traveling to infinity and traveling to negative infinity on the opposite sides here. So as a result, we actually have to solve two different inequalities. This one can't be written as a sandwich. It has to be two separate ones. In one inequality, a is going to be less than negative b. And in the other inequality, a is going to be greater than positive b. So that one does need to get split up into two inequalities because it doesn't form a sandwich between the two things. It actually ends up being the two tail ends, which are intervals that aren't connected. And very similar, if the distance between a and 0 is greater than or equal to b, we're just going to change this to square brackets, but essentially the same picture. The two intervals are not attached. And the result here would be two inequalities, a less than or equal to negative b, or a greater than or equal to positive b. Now I've drawn all of these number lines as if b was a positive value, but b is any expression. And then an expression itself could end up being negative, in which case negative b would be on the right-hand side. As a quick example, if we have the absolute value as x minus 5 less than 8, then that tells us that x minus 5 is going to be sandwiched between negative 8 and positive 8. And we can add 5 to all three expressions, negative 3 less than x less than 13. And hopefully that makes sense, because this can also be thought of as the distance between x and 5 is 8 units. Take 5, go 8 units left and get negative 3. Take 5 and go 8 units right and we get 13. If we switch this to a greater than or equal to sign, and the absolute value of 2x minus 1 greater than or equal to 3, now we have two inequalities. We would say that 2x minus 1 could be less than or equal to negative 3, or we can have 2x minus 1 be greater than or equal to positive 3. And in both of these inequalities, we can add 1, and then in both inequalities, we can divide by 2. And x could be less than or equal to negative 1, or x could be greater than or equal to 2. And both of these solutions should be better written in interval notation. And of course, keep in mind that infinity always has round brackets, and if x can be in more than one different interval, then we should union the two intervals together. Okay, well that gives you at least a few examples of different kinds of inequalities, and depending on the absolute value, that can maybe be involving linear inequalities at the end, or could be even worse. Perhaps you have an absolute value inequality and that breaks up into some quadratics. Really just make sure that you have a good checklist in front of you so that you can understand what type of inequality you have and how to tackle it. And from then on, it's just practice. Thanks for watching, and I'll see you guys in the next video.